हेलो फ्रेंड्स, तो राना अकेडमी में आपका स्वागत है। हमने स्टार्ट किया 11th क्लास की वन शॉट सीरीज, जिसमें हम स्टार्ट करेंगे अब 5 यूनिट्स थर्मोडायनामिक्स। और इट इज़ द ओनली फिजिकल theory ऑफ यूनिवर्सल कंटेंट concerning with which I am convinced that within the framework of the applicability of its basic concepts it will never be overthrown. Albert Einstein. Chemical energy stored by molecules can be released as heat during chemical reactions when a fuel like methane, a cooking gas, or coal burns in the air. And the chemical energy may also be used to do mechanical work when a fuel burns in an engine, or to provide electrical energy through a galvanic cell, like the dry cell. Thus, various forms of energy are interrelated, and other under certain conditions, these may be transformed from one from into another. The study of these energy transformations forms the subject of matter with energy changes of macroscopic systems involving a large number of molecules rather than microscopic systems containing a few molecules. Thermodynamics is not concerned about how and at what rate these energy transformations are carried out, but is based on initial and final states of a system undergoing the change. Laws of thermodynamics apply only when a system is in equilibrium state. Macroscopic properties like pressure and temperature do not change with time for a system in equilibrium state. In this unit, we would like to answer some of the important questions through thermodynamics, like how do we determine the energy changes involved in chemical reaction process, what will it occur or not, what drives a chemical reaction process, to what extent do the chemical reactions proceed. Thermodynamic terms, we are interested in chemical reactions and the energy changes accompanying them, or this we need to know certain thermodynamic terms. These are discussed below. The system and the surroundings. The system in thermodynamics refers to that part of universe in which observations are made on and remaining universe constitutes the surroundings include everything other than the system and the surroundings together constitute the universe. The universe is equal to the system plus the surrounding. However, the entire universe other than the system is not affected by the changes taking place in the system. Therefore, for all practical purposes, the surroundings are that portion of the remaining universe which can interact with the system, usually the region of space in the neighborhood of the system constitutes its surroundings. For example, if we are studying the reaction between two substances A and B kept in a beaker, the beaker containing the reactions mixture is the system, and that the room where the beaker is kept is the surroundings. Figure 5.1, system and the surroundings. Note that the system may be defined by physical boundaries like beaker or test tube, or the system may simply be defined by a set of Cartesian coordinates specifying a particular volume in space. Then it is necessary to think of the system as separated from the surroundings by some sort of wall, which may be real or imaginary. The wall that separates the system from the surroundings is called boundary. This is designed to allow us to control and keep track of all movements of matter and energy is in or out of the system. The types of the system, we further classify the systems according to the movements of matter and energy in or out of the system. A open system, in an open system there is exchange of energy and matter between the system and surroundings. 5.2a, the presence of the reactants in an open beaker is an example of the open system. Here the boundary is an imaginary surface enclosing the beaker and reactants. Closed system, in a closed system there is no exchange of matter but exchange of energy is possible between system and the surroundings. The presence of reactants in the closed vessel made of conducting material, example copper and steel, is an example of closed system. Isolated system, in an isolated system there is no exchange of energy or matter between the system and the surroundings. The presence of reactants in the thermos flask or any other closed insulated vessel is an example of an isolated system. The state of the system, the system must be described in order to make any useful calculations by specifying quantitatively each of the properties such as its pressure, volume and the temperature, as well as the composition of the system. We need to describe the system by specifying it before and after the change. You would you would recall from your physics course that the state of the system in mechanics is completely specified at a given instant of time by the position and velocity of each mass point of the system. In thermodynamics, a different and much complex concept of the state of a system is introduced. It does not need a detailed knowledge of motion of each particle because knowledge of motion such as of each particle because we deal with the average measurable properties of the system. We specify the state of the system by state functions and state variables. The state of this thermodynamics system is described by its measurable or macroscopic properties. We can describe the state of a gas by quoting its pressure, volume and temperature, amount, etc. variables of PVT called state variables and state functions because their values depend only on the state of the system and not on how it is reached. In order to completely define the state of the system, it is not necessary to define all the properties of the system as only a certain number of properties can be varied independently. This number depends on the nature of the system. Once there is the minimum number of macroscopic properties are fixed, others automatically have definite values. The state of the surroundings can never be completely specified. Fortunately, it is not necessary to do so. The internal energy as a state functions when we talk about our chemical system are losing or gaining energy. We need to introduce a quantity which represents the total energy of the system. It may be chemical, electrical or mechanical or any other type of energy. You may think of the sum of all these visual all of these is the energy of the system. In thermodynamics, so we call it the internal energy U of the system, which may be changed when heat passes into or out of the system. Second, work is done on or by the system. Third, matter enters or leaves of the system. These systems are classified accordingly as you have already studied in first section 5.1. Work, heat. The general case. Applications. Many chemical reactions involve the generation of gases are capable of doing mechanical work or the generation of heat. It is important for us to quantify these changes and relate them to the changes in the internal energy. Let us see how work. Now, first of all, let us concentrate on the nature of the work. Nature of a work system can do. We will consider only mechanical work, that is pressure volume work. For understanding pressure volume work, let us consider cylindrical cylinder which contains 1 mole of an ideal gas fitted with the functionless position piston. Total volume of the gas is V, and pressure of the gas inside is P. If the external pressure is Px, which is greater than P, piston is moved inward till the pressure inside becomes equal to Pex. Let this change be achieved in a single step, and the final volume of Vf during this compression. Suppose piston moves distance. Now T is cross sectional area of the piston is A. Then volume change is equal to delta V, Vf minus Vi. We also know pressure, force upon area. Force on the piston, the Pex is dot A. And if W is the work done on the system by movement of the piston, then Pex dot minus delta V is equal to P and minus Pex delta V is equal to minus Pex V final minus V initial. The negative sign of this expression is required to obtain conventional sign of VW, which will be positive. It indicates that in case of compression, work is done on the system. Here Vf minus Vi will be negative, and negative multiplied by negative will be positive. Hence, the sign obtained for the work will be positive. The process or change is said to be reversible if a change is brought out in such a way that the process could at any moment be reversed by an infinite similar change. A reversible process proceeds infinitely slowly on by a series of equilibrium states, such that system and the surroundings are always in near equilibrium with each other. Process other than the reversible processes are known as irreversible processes. In chemistry, we face problems that can be solved if we relate the work for term so the internal pressure of the system. We can relate work or to internal process pressure of the system under reversible conditions. Isothermal and free expansion of an ideal gas. For isothermal, T is equal to constant expansion of an ideal gas into vacuum. W is equal to 0 since Pex is equal to 0. Also, Joule determined experimentally that Q is equal to 0, therefore the delta U is equal to 0. Equation 5.1 delta U is equal to Q plus W can be expressed for isothermal irreversible and reversible changes as follows. For isothermal irreversible changes, Q is equal to minus W is equal to Px V final minus V initial. For isothermal reversible change, Q is equal to minus W is equal to NRT. Now in V final minus V initial, V final upon V initial. 2.303 NRT log Vf upon Vi. For adiabatic change, Q is equal to 0, delta U is equal to Vex. Problem 5.2. 2 liters of an ideal gas at a pressure of 10 atm expands isothermally at 25 degrees Celsius into a vacuum until its total volume of is 10 liter. How much heat is absorbed and how much work is done in the expansion solution? Now we have Q is equal to minus W is equal to P x 10 minus 2 is equal to 808 is equal to 0. No work is done, no heat is absorbed. Problem 5.3. Consider the same expansion but this time against the constant external pressure of 81 atm. We have Q is equal to minus W is equal to PEX into 8 is equal to 8 liter per atm. Problem 5.3. Consider the expansion given in problem 5.2 for 1 mole of an atom, 1 mole of an ideal gas, a conductor reversible solution. We have Q is equal to minus W is equal to 2.303 nRT log VA final minus V initial, VA final upon V initial 2.303 into 1 into 0.8206 into 298 into log 10 upon 2. Final answer is 393.66 liter per atm. Enthalpy H useful new state function. Delta H is negative for exothermic reactions which involve heat during the reaction, and delta H is positive for endothermic reactions which absorb heat from the surroundings. Problem 5.5. If water vapor is assumed to be the perfect gas, molar enthalpy change for vaporization of 1 mole of water at 1 bar and 100 degrees Celsius is 41 kilojoule per mole. Calculate the internal energy change when 1 mole of water is vaporized at 1 bar pressure and 100 degrees Celsius. Solution: the change H2O then gives H2O gram. Delta H is equal to delta U plus delta NGRT or delta VU is equal to delta H minus delta NGRT. Substituting the values we get delta U is equal to 41 kilojoule per mole minus 1 into the 8.3 joule per mole per Kelvin into 373 per Kelvin. 441.00 kilojoule per mole minus 3.096 kilojoule per mole is equal to 37.904 kilojoule per mole. Extensive and intensive properties. In thermodynamics, the distinction is made between extensive properties and intensive properties. An extensive property is a property whose value depends on the quantity of or size of the matter present in the system. For example, mass, volume, internal energy, enthalpy, heat capacity, etc. are extensive properties. There's those quantities which do not depend on the quantity or size of matter present are known as intensive properties. For example, temperature, density, pressure, etc. are intensive properties. A molar property xm is the value of the extensive property x of the system of for 1 mole of the substance. If n is the amount of matter, xm is equal to x upon n is independent of the amount of matter. Other examples are the molar volume Vm and molar heat capacity Cm. Now let us understand the distinction between the extensive and intensive properties by considering a gas enclosed in a container of volume V and at temperature T. Now let us make a partition such that volume is half each part 5.6 b now has one half for the original volume V by 2, but the temperature will still remain the same, that is T is the T. It is clear that volume is an extensive property and temperature is an intensive property. Uh, Heat capacity. In this subsection, let us see how to measure heat transferred to a system. This heat appears at the rise in temperature of the system. In case of heat absorbed by the system, and the increase of temperature is proportional to the heat transferred. Q is equal to coefficient into delta T. The magnitude of this coefficient depends on the size, composition and nature of the system. We can also write it as Q is equal to C delta T. The coefficient C is called the heat capacity. Thus we can measure the heat supplied by monitoring the temperature rise, provided we know that heat capacity. When C is large, a given amount of heat results in only a small temperature rise. Water has a large heat capacity, that is a lot of energy is needed to raise its temperature. C is directly proportional to amount of substance. The molar heat capacity of a substance, Cm is equal to C upon N, is the heat capacity for 1 mole of the substance, and it's the quantity of heat needed to raise the temperature of 1 mole of the 1 degree Celsius or 1 Kelvin. Specific heat, also called specific heat capacity, is the quantity of heat required to raise the temperature of the unit mass of the substance by 1 degree Celsius. For finding out the heat temperature required not to raise the temperature, for example, for sample we multiply the specific heat of the substance C by the mass is small m, and the temperature required change delta T as small q is equal to C into small m into delta T is equal to C delta T. The relationship between Cp and Cv for an ideal gas, Cp is equal to Cv plus R, Cp minus and Cv is equal to capital R. Measurement of delta U and delta H calorimetry. Delta U measurements, delta H measurements. Problem 5.6. 1 gram of graphite is burnt in a bomb calorimeter in excess of oxygen at 298 Kelvin and 1 atmospheric pressure according to the equation. C plus O2 and then gives CO2. During the reaction, temperature rises from 298 Kelvin to 299 Kelvin. If the heat capacity of the bomb calorimeter is 20.7 kilojoule per Kelvin, what is the enthalpy change for the above reaction at 298 Kelvin at 1 atm? Solution. Suppose Q is the quantity of heat from the reaction mixture and Cv is the heat capacity of the calorimeter. Then the quantity of heat absorbed by the calorimeter Q is equal to Cv into delta T. Quantity of heat from the reaction will have the same magnitude but opposite sign because the heat loss by the system reaction mixture is equal to the heat gained by the calorimeter. Q is equal to minus Cv into delta T. Here negative sign indicates the exothermic nature of the reaction. Thus delta VU for the combustion of the 1 gram of graphite is equal to minus 20.7 kilojoule per Kelvin. For combustion of 1 mole of graphite, 12.0 gram per mole into minus 20.7 kilojoule upon 1 gram is equal to minus 2.48 into 10 to the power 2 kilojoule per mole. So enthalpy change delta H of a reaction enthalpy. Standard enthalpy of reactions. The standard enthalpy of reactions is the enthalpy change for a reaction when all the participating substances are in their standard states. The standard state of a substance at the specified temperature is its pure form at 1 bar. The enthalpy changes during phase transformations. The enthalpy change that accompanies a melting of 1 mole of solid substance in a standard state is called standard enthalpy of fusion or molar enthalpy of fusion, delta H. Amount of heat required to vaporize 1 mole of liquid at constant temperature and under standard pressure is called its standard enthalpy of vaporization or molar enthalpy of vaporization, delta vaporization H W capital H. Standard enthalpy of sublimation, delta capital H, is the change of enthalpy when 1 mole of solid substances sublimes at the constant temperature and under standard pressure 1 bar. Problem 5.7. The swimmer coming out from the pool is covered with the film of water weighing about 18 grams. How much heat must be supplied to evaporate this water at 298 Kelvin? Calculate the internal energy of vaporization at 298 Kelvin. Delta vaporization capital H for water at 298 Kelvin is equal to 44.01 kJ per mole. Solution, we can say, represent the pressure process of evaporation as to H2O 1 mole is equal to H2O 1 mole gram. Number of moles in 18 gram H2O is 18 gram upon 18 gram 18 per mole 1 mole. Heat supplied to evaporate 18 gram water at N into delta evaporation capital is 1 mole is equal to 1 mole into 44 kilojoule per mole, 44 kilojoule. Assuming steam behaving as an ideal gas, delta vapor U capital U is equal to delta vapor delta capital S minus P delta V is equal to delta Vp vapor capital H minus delta nRT delta vapor capital H V minus delta nRT is equal to 44.101 kilojoule minus 8.314 joule per Kelvin per mole. 298 Kelvin into 10 to the power minus 3 kilojoule per mole per joule. Delta vapor V is equal to 41.53 kilojoule. Problem 5.8. Assuming the water vapor how to be a perfect gas, calculate the internal energy change when 1 mole of water at 100 degrees Celsius and 1 bar pressure is converted to ice at 0 degrees Celsius. Given the enthalpy of fusion of ice is 6 kilojoule per mole. The heat capacity of water is 4.2 joule per gram per degree Celsius. The change takes place as follows: 1 mole H2O then gives 1 mole enthalpy change to delta H. 1 mole H2O then gives 1 mole H2 0 degrees Celsius. Enthalpy change to delta H2 delta H is equal to delta H1 plus delta H2. Delta H2 is equal to minus 6 kilojoule per mole. Delta H1 is equal to minus 7.56 kilojoule per mole. Therefore, delta H is equal to minus 13.56 kilojoule per mole. There is negligible change in the volume during the change from liquids to solid state, and therefore delta P delta V is equal to delta NGRT is equal to 0. Delta H is equal to delta U is equal to minus 13.56 kilojoule per mole. Standard enthalpy of formation Table 5.2 standard molar enthalpy formation of delta H on delta FH at 298 Kelvin of a few selected substances. Standard enthalpy of formation and the standard enthalpy change for the formation of 1 mole of a compound from its elements in their most stable states of aggregation, also known as reference state, is called standard molar enthalpy of formation. Its symbol is delta FH. Thermochemical equation. Hess's law of constant heat summation. If a reaction takes place in several steps, then its standard reaction enthalpy is the sum of the standard enthalpies the intermediate reactions into which the overall reaction may be divided at the same temperature. Enthalpies for different types of reactions. Standard enthalpy of combustion. Problem 5.9. The combustion of 1 mole of benzene takes place at 298 Kelvin and 1 atm. After combustion, CO2 gram of H2O liter are produced and 3267 kilojoule of heat is liberated. Calculate the standard enthalpy of formation delta FH of benzene. Standard enthalpies of formation of CO2 gram and OH2O liquid are minus 393.5 kilojoule per mole and minus 285.83 kilojoule per mole respectively. The formation or reaction of benzene is given by 6 carbon graphite plus 3H2 gram and then gives 6 C6H6 liter. Now delta FH is equal to question mark. The enthalpy of combustion of 1 mole of benzene is C6H6 plus 15 by 2 O2 then gives 6 CO2 plus 3 times H2O. And delta CH is equal to minus 3267 kilojoule per mole. The enthalpy of formation of 1 mole of CO2 C graphite plus O2 then gives CO2 delta F H is equal to minus 393.5 kilojoule per mole. The enthalpy of formation of 1 mole of H2O is H2 plus half O2 then gives H2O. Delta CH is equal to minus 285.83 kilojoule per mole. Multiplying equation 3 by 6 and equation 4 by 3, we get C6 graphite plus C6 CO2 then gives 6 times CO2. Delta FH is equal to minus 2361 kilojoule per mole. Delta H2 gram plus 3 by 2 O2 gram plus then gives 3 times H2O liquid. Delta F H and is equal to minus 857.49 kilojoule per mole. Swimming up the above two equations. 6 graphite C6 graphite plus 3 times H2 gram plus 15.2 O2 then gives 6 times CO2 plus 3 times H2O. Delta FH is equal to minus 32.184.49 kilojoule per mole. Reversing equation 6 times CO2 plus 3 times H2O then gives C6H6 liquid plus 15.2 O2. Delta FH is equal to minus 32.67 kilojoule per mole. Adding equations 5 and 6, we get C6 graphite plus 3 times H2 then gives C6H6. Delta FH is equal to minus 48.51 kilojoule per mole. Enthalpy of atomization symbol delta H. Bond enthalpy symbol delta bond here capital H. Diatomic molecules, polyatomic molecules. Table 5.3 some mean the single bond enthalpies in kilojoule per mole at 298 Kelvin. 5.3b. Some mean some multiple bond enthalpies in kilojoule per mole at 298 Kelvin. Lattice enthalpy. Ionization energy and electron and affinity. Ionization energy and electron affinity are defined at absolute zero, not any other temperature. Heat capacities for the reactants and the product have to be taken as into account. Enthalpies of reactions for M is equal to M positive plus electron for ionization. M plus electron is equal to M minus for electron again. Temperature capital T is delta H capital T is equal to delta R is capital H into 0 plus into T2 0 delta F Cp delta T. The value of Cp for each species in the above reaction is 5/2 capital R. Cv is equal to 3/2 capital R. Cp is equal to 5/2 capital R. For ionization, Cp is equal to minus 5/2 capital R. For electron gain, therefore the delta H ionization enthalpy is 0. E naught ionization energy is equal to ionization energy plus 5/2 RT. Delta H for electron gain enthalpy minus the electron affinity minus 5/2 RT. Enthalpy of solution symbol delta of solution I capital H. Enthalpy of dilution, spontaneity, and decrease in enthalpy as criterion for spontaneously, entropy and spontaneity. Problem 5.10. Predict in which of the following entropy decreases. The liquid crystallizes into a solid. Temperature for the crystalline solid is raised from 0 Kelvin to 115 Kelvin. 2 NH sodium 2 NaHCO3 then gives 2 times Na2CO3 solid plus CO2 gas plus H2O gram. H2 then gives 2 times H. Solution after freezing the molecule attain entropy decreases 0 Kelvin. The constituent properties of atom static and entropy is minimum. The thermodynamic, if temperature is raised to 115 Kelvin, they begin to move and oscillate about their equilibrium positions, and the lattice and system becomes more disordered. Therefore entropy increases. Reactant NaHCO3 is solid and it has low entropy. Among products there are one solid and two gases, and therefore the products represent a condition of higher entropy. Here one molecule gives two atoms, that is number of particles increases, leading to more disordered state. 2 moles of capital H atom have higher entropy than 1 mole of dihydrogen molecule. Problem 5.11. For oxidation of iron, 4 times ferrous plus 3 times O2 then gives 2 times FeCO3. FeO3 entropy changes minus 549.4 joule per Kelvin per mole at 298 Kelvin. In spite of an negative entropy change of this reaction, why is the reaction spontaneous? Delta H now for this reaction is 1000 minus 1648 into 10 to the power 3 joule per mole. Solution. One decides the spontaneity of a reaction by considering delta S y plus delta S y is for calculating absorbed for the substituents, which is equal to delta minus delta of H at temperature delta T. Entropy change of the surroundings is delta S is equal to minus delta R capital H upon capital T at constant pressure minus 1684 48 into 10 to the power 3 joule per mole upon 298 Kelvin, 5530 joule per Kelvin per mole. Gibbs energy and spontaneity, entropy and the second law of thermodynamics, absolute entropy and third law of thermodynamics. The entropy of any pure crystalline substance approaches zero as the temperature approaches absolute zero. This is called third law of thermodynamics. Gibbs energy change and equilibrium. Table 5.4 Effect of temperature on spontaneity of reactions. 5.12 Problem. Calculate the delta G naught for conversion of oxygen to ozone 3 by 2 O2, then gives O3 at 298 Kelvin. If Kp for this conversion is 2.47 into 10 to the power minus 29. Solution, we know G delta G of is equal to minus 2.303 RT log Kp, and R is equal to 8.314 joule per Kelvin per mole. Therefore, delta Fg is equal to 2.303 8.314 joule per Kelvin per mole into 298 Kelvin log 2.47 into 10 to the power minus 29 1,63,000 joule per Kelvin joule per mole, 163 Kelvin kilo joule per mole. Problem 5.30. Find out the volume value of equilibrium constant for the following reaction at 298 Kelvin. 2 times NH3 plus CO2 then gives NH2 CONH2 aqueous plus H2 later. Standard Gibbs energy change delta G at the given temperature is minus 13.6 kilojoule per mole. Solution, we can know log K is equal to minus delta delta F G upon 2.303 RT. Hence K is equal to antilog 2.38 is equal to 2.4 into 10 to the power 2. Problem 5.14 at 60 degrees Celsius. Definition, on the tetroxide is 50% as dissociated. Calculate the standard free energy change at this temperature and at 1 atmosphere. Solution, N2O4 gram then gives 2 times NO2. If N2O4 is 50% as dissociated, the molar fraction of both the substance is given by X and N2Cl 4 is equal to 1 minus the 0.5 upon 1 plus 0.5 X NCl2 is equal to 2 into 0.5 upon 1 plus 0.5 ion N2O4 P N2O4 is equal to 0.5 upon 1.5 into 1 atm P NO2 is equal to 1 upon 1.5 into 1 atm. The equilibrium constant Kp is given. Kp is equal to P upon NO2 upon N2O4 is equal to 1.5 upon 1.5 square 1 into 0.5 is equal to 1.33 atm. Says delta G is equal to RT minus RT in Kp. Delta G is equal to minus 8.314 joule per Kelvin per mole and to 313 Kelvin and to 2.303 into 0.1239 is equal to minus 763.8 kilojoule per mole. Thermodynamics chemistry. Thermodynamics deals with the energy changes in chemical and physical processes and enables us to study these changes quantitatively and to make useful predictions Now, for these purposes, we divide the universe into the system and the surroundings. Chemical or physical processes lead to evolution or absorption of heat, part of which may be converted into work. Now, these quantities are related through the first law of thermodynamics, by delta U is equal to Q plus V W. Delta U change in internal energy depends on initial and final states only, and is the state of function, whereas Q and W depends on the path and are not the state functions. We follow signs conventions of Q and W by giving the positive sign to these quantities. When these are divided to the system, we can measure the transfer of heat from one system to another, which causes the change in the temperature. The magnitude of rise is in temperature depends on the heat capacity of a substance. Therefore, the heat absorbed by or evolved is Q is equal to, say, delta T. Work can be measured by W is equal to minus P x delta V. In case of expansion of gases under a reversible process, we can put if Px is equal to P for infinite seminar. Changes in the volume making W x V is equal to minus P delta V. In this condition, we can use gas equation. PV is equal to nRT at constant volume. W is equal to d0 and delta V U is equal to QV, heat transfer at constant volume. But in study of chemical reactions, we usually have constant pressure. We define it another state function, enthalpy change. Delta H is equal to delta U plus nRT can be found directly from the heat changes at constant pressure. Delta H is equal to QR. There are varieties of enthalpy changes of phase such as melting, vaporization, and sublimation usually occur at constant temperature and can be characterized by enthalpy changes which are always positive. Enthalpy formation, combustion, and other enthalpy changes can be calculated using Hess's law. Enthalpy change for chemical reactions can be determined by delta H is equal to summation of AF delta F H and minus the equation summation B delta F H evaporation in gases state by delta H of is equal to summation of bond enthalpies of reactants minus summation of bond enthalpies of the products. First law of thermodynamics does not guide us about the direction of chemical reactions. That is what is the driving force of a chemical reaction for isolated systems. Delta U is equal to 0. We define another state of functions. The entropy for this purpose, entropy is a measure of disorder or randomness of for a spontaneous change. Total entropy change is positive. Therefore, for an isolated system, delta U is equal to 0, delta S is greater than 0. So, entropy change distinguishes a spontaneous change, while energy change that does not. Entropy changes can be measured by the equation delta S is equal to QERV upon T. Now, for reversible forces, QREV upon T is independent of path. Chemical reactions are generally carried out at constant pressure, so we define it another state functions Gibbs energy capital G, which is related to entropy and enthalpy changes of the system by the equation delta G is equal to delta H minus T delta S. For the spontaneous change, delta G is less than 0 and at equilibrium delta G is equal to 0. Standard Gibbs energy change is related to equilibrium constant by delta G is equal to minus RT in LK in K. K can be calculated from this equation if you know delta G, which can be found from delta G delta H of minus T delta S. The temperature is an important factor in the equation. Many of the reactions which are non-spontaneous at a low temperature are made spontaneous at high temperature for systems having positive entropy or reactions. सो हमने 11th क्लास की केमिस्ट्री स्टार्ट की है, जिसमें हमने वन शॉट सीरीज स्टार्ट की है. प्लीज़ इस वीडियो को शेयर कीजिएगा, जिसमें आपको प्रैक्टिस के लिए बहुत ज़्यादा इजी होगा और रिवीजन के लिए भी बहुत ज़्यादा इजी जाएगा. थर्मोडायनेमिक्स हमारा यूनिट 5 है, 11th क्लास की केमिस्ट्री का. थर्मोडायनेमिक्स टर्म्स द सिस्टम एंड सराउंडिंग, टाइप्स ऑफ सिस्टम, ओपन सिस्टम, क्लोज सिस्टम, isolated system, the state of system, the internal energy as the state functions, work, heat, the general case, applications, work, isothermal and free expansion of an ideal gas, enthalpy, the use of new state functions, extensive and intensive properties, heat capacity, the relationship between Cp and Cv for an ideal gas, measurement of delta U and delta H calorimetry, delta U measurements, delta H measurements, enthalpy change and delta H are of for reaction and reaction enthalpy, the standard enthalpy of reactions, enthalpy changes during phase transformation 5.1, standard table 5.1, and standard enthalpy changes or fusion of vaporization. Table 5.2, standard molar enthalpies of formation delta FH is at 298 Kelvin of a few selected substances. Standard enthalpy of formation, thermochemical equations, Henry's law of constant heat summation, enthalpies for different types of reactions, standard enthalpy of combustion, enthalpy of atomization, bond enthalpy. Table 5.3, some mean single bond enthalpies in kilojoule per mole at 298 Kelvin. Some mean enthalpy bond enthalpies in kilojoule per mole at 298 Kelvin. Table 5.3b, lattice enthalpy. Then enthalpy of solution, symbol for delta solution, capital H. Enthalpy of dilution, spontaneity is decrease in enthalpy and criterion for spontaneity, entropy and spontaneity, Gibbs energy and spontaneity, entropy and second law of thermodynamics, absolute entropy and third law of thermodynamics, Gibbs energy change and equilibrium. Table 5.4, effect of temperature on spontaneity of reaction. Then summary. प्लीज़ इस वीडियो को शेयर कीजिएगा एंड लाइक कीजिएगा. राणा एकेडमी इस चैनल को सब्सक्राइब भी कीजिएगा, क्योंकि यहाँ पर बहुत सारे वीडियोस हैं वन शॉट सीरीज़ के जो आपको बेनिफिट्स देंगे रिवीजन में. थैंक यू सो मच फॉर वॉचिंग. थर्मोडायनेमिक्स 11th क्लास केमिस्ट्री ख़त्म होता है यहाँ पर. प्लीज़ लाइक शेयर एंड सब्सक्राइब.